All right. Hi, everyone. Welcome to the second part of lecture 17. And now we're going to talk about paging and caching. Okay. So, all right. So what is the online paging problem? Right. So we know that computer memory is hierarchical, right? So when you have your computer, we can model our memory essentially with there is your cache, which has some lines. And then after cache, we have a bigger memory, which is the L1, which is, a secondary layer of cache, like in modern computers, right? And then we have L2, which is also bigger, and all of these have lines. That's how we can model them. And let's say, we have main memory, which is really, really big, but really, really slow. Right? And the idea is as you go from left to right, what do? You have slower access, right? It's really slow to access things from the bigger memory, but you have more memory. Right? So this is how like the memory works in our computer, right? And we have lots of layers these days, like things are very optimized, but this is how it works. And then what is the well, as we said, like each layer of memory, we can think of it as an array with a certain number of pages, right? And hence that's why we have the online paging problem, okay? Because we're going to deal with these pages. So if you saw the drawing, like each memory can just be modeled by, I have each of these lines here is going to be a page, right? And whenever you fetch something from memory, okay, you're going to fetch and you're going to put it in a page, right? In a page or two or so on, right? So we're but let's just assume for simplicity that whenever you fetch something, you fetch one thing from there and you put it in the page. Okay, so the page can fit whatever, like one page can fit whatever data request you have during your algorithm. Okay, does that make sense? All right. So, okay, so the page, what does it store? It stores the content of the item and its location in main memory. So it knows what the item is, and it knows, oh, where is it located in main memory? Because if you need to write it, if you need to write on it, you have to write and you have to go back to main memory and update it, right? All right, so when we get a request, right? And request here is equivalent to like what we said about an event when we're talking about our online jargon, right? Like the event here will be a request, right? So when we get a request for a page, right? Someone will say, okay, fetch me that page in memory, right? What do? Well, we first look up in cache, because if a person is requesting something in memory that's already in cache, we don't need to go to the main memory, right? So we first go to cache. If it's not in cache, we look it in L1, and then we look it in L2, and then we look it in memory, right? So, all right, if the request is in the cache already, then we have a hit. And then we can say that the request takes negligible time, right? It's kind of like you go to your browser, like you go to a page you've been before, like boom, it loads automatically, right? But, and here in negligible extra time, we can also copy new data to location and time, okay? So the main problem is to fetch the data from slower memory, okay? So the thing that takes most time, is fetching data from slower memory. Okay, so that would be our assumption here. And okay, now if the cache is full, now suppose, oh yeah, sorry, I forgot to say that otherwise we have a miss, right? So if the request is not in cache, then we have a miss. That's a cache miss. And if we have a miss, what do? We have to fetch the data from the slower memory, and we have to write it, right? And here, let me just add that we also have to write the data, the new data, in cache, right? So whenever someone, because the cache is kind of giving to you, like kind of the most recently, the most hot things that you have accessed, right? That's what your cache kind of holds. Does that make sense? So your last requests will have to be stored in the cache. Yeah? Okay, so, all right. So now what happens? So here's the thing. The only thing that your algorithm will be concerned then, right, is, okay, if you make a request, if it's not in cache, I have to fetch it from somewhere. Now, if I have empty space in my cache, I can just put it in the empty space, right? But if your cache is full, then we need to delete an old entry before copying the new data. Does that make sense? So all we have to do is, the main question that we need to address here is which entry of the cache to delete. Does that make sense? And you can clearly see that this is an online setting because your computer can certainly not see into the future. Not even you can see into the future, right? So the list of requests that you're going to make, right? The computer has to make a decision on the spot. You made a request. If it has to fetch it from slower memory, it will have to put it in the cache. Now the question is where and what do I evict? Okay. So, all right. So what is the cost function? So the cost function for us here will be exactly the number of cache misses. Okay. We want to minimize the number of cache misses, right? All right. And again, let's just make another simplification. Let's suppose that we only have cache and main memory. Okay. Like this is just a basic simplification. It doesn't get much harder. It's just more cumbersome, the math. Okay. So, all right. So what are the common heuristics to use the cache, to use for which page to evict, right? Which page are we going to delete? So there's the least recently used heuristic, which is what? Well, the algorithm is simply, well, whenever I have to delete something from cache, we delete the page in cache whose most recent request appeared furthest in the past, right? Hence the name least recently used. The other one is a random, like, okay, if I have to delete something, let's just delete the random page. Okay. And the third one is the first in, first out. So what do? We delete the page that has been in cache the longest. No matter if I used it more recently, if it was there the longest, I'll delete that page. Does that make sense? Okay. And there's another one, which is the least frequently used, right? Which is what? Well, what we do is we keep the frequency, a tab on the frequency of how many requests I had from each page. And then I'm going to delete the page which has been requested least often, because suppose that you just requested the page once, and then you request a bunch of other times like the other pages, and you didn't request this page again, right? So even though you may have kind of another page may have been in the cache longest, it's probably there for a reason, because you have been requesting that page like crazy, right? So this is another heuristic. And here's the thing. Okay, so today what we're going to do is we're going to analyze the least recently used heuristic, and we're going to assume that the size of our cache is k pages. Okay, we're going to have this k as the number of pages that we have in our cache. Okay, so if your cache has k pages, here's what we know. Okay, the first three algorithms, they are actually k competitive, and the least frequently used algorithm is actually not competitive at all. Okay, so where k is the size of our cache. Okay, and today we're only going to analyze the first one. Okay. All right, so here's our analysis, right? So for a cache of size k, we want to say that the LRU is k competitive. Okay, so how do we do to upper bound this? To upper bound this, what we're going to do is we're going to divide our input sequence into phases. Okay, and what is the phase? The first phase will start immediately after our algorithm first faults, and then it will end right after the algorithm faults k more times. Does that make sense? So right after I first fault, I start my first phase. And then I'm going to count, okay, how many times in this phase I have faulted. Once I fault k times, then I start, right after I fault k times, I start the second phase. Does that make sense? And then we keep going. So this will be the phases. Okay, so we're going to use this to prove that the algorithm is k competitive. All right, And here, and why are we dividing this by phases? And we're going to prove that the optimum algorithm will fault at least once per phase, right? So this gives us our competitive analysis, right? Because in each phase, opt faults once, and our algorithm faults exactly k, right? So the cost of our algorithm for any sequence S over the cost of opt has to be less than or equal to k over 1. Does that make sense? So we have the k competitiveness. Does that make sense? So all we need to do is to prove that opt will fault at least once per phase. So step 2 is all we need to do. Okay, now let's see how to do this. Okay, as we saw, like this gives us like the k approximation, right? Like the k competitiveness, which is what we want. Okay, so let's see an example for cases, right? Of phases, right? For k, let's say equals to 3, and let's say that this is the request for pages, right? So this is the request sequence. Request sequence for pages. Okay, so let's see how this example goes. Our phases will be exactly this. Well, I'll have, remember, like at first my cache is my cache is empty. So no matter what I request, I'm gonna have a cache miss because there's nothing in my cache. Does that make sense? So in this first case, this is my first miss, always. Because our cache is empty, right? So yeah, here, sorry, I forgot to say that our assumption here is that we start with empty cache. Okay. So, all right. And we start with empty cache, and so does opt, right? Like, so any algorithm, right? Like that's, now, all right. So, okay. So the first mistake, like, sorry, the first cache miss, right, happens right away in the first request because our cache is empty. And then what do? Well, we have a cache of size 3. So what's going to happen? Well, okay. So if I request 1 again, I have no miss, right? So, and then when am I going to have a miss again? I'm going to have a miss again on 2. So that's another cache miss. And then I request 2 again, no cache miss. 1 again, no cache miss. Once I request 3, I have my second cache miss because 3 was not in the cache before. And then 4 will be another cache miss. So this will be 3 cache misses. Does that make sense? And then this start in the new phase. And the new phase here, I have the other bracket, right? Like the parenthesis here is, okay, so now what was my cache once I ended, right? Like, remember, we're doing the least recently used, right? So what was the least recently used so far? Okay, let me actually go to the other page because I have the example here, right? So at first, my cache was empty. So let's just say that the cache is empty. Our cache is of size 3. Let me just put like 3 here like this, right? And then in the first step, my cache becomes 1, 0, like empty. And then once I do 2, like in this step, my cache will become 1, 2, empty. And then once I go to 3, my cache will become 1, 2, 3. And once I come 4, so this was 2, and then this was 3. And then once I receive 4, which one do I use? Once I receive 4, which one should I evict? Well, who was the least recently used in our setting, right? The least recently used in our setting was exactly 2, right? So I have to evict 2. So I have 1, 4, 3, right? And then, okay, and then I'm going to request 3 again, but nothing happens. Now, if I request 2, I have another cache miss, right? So this is when the new cache miss will happen. And then who am I going to evict? Who was the least recently used in our cache here? The least recently used was 1, right? So I'm going to evict 1. So I have 2, 4, 3. And now I request 4, I have no miss. I request 5 and 6, I have 2 misses. So once I request 5, I'm going to have my miss. Now, who from 2, 4, and 3 is the least used? Least used it was 3. So then 5 goes here, 4 stays in the cache, 2 stays in the cache. And then on 6, I have my third cache miss. 5. So you can see that each phase I'm making exactly k misses, right? So by definition of our phase. Now, who exits the cache here? Well, 5 and 4 were recently used. So 5 and 4 stay, and then 2. And so on. Does that make sense? Is this example clear?
I think you meant to write a 6 instead of 2 there.
Oh, yeah, I meant to write a 6. Thank you. All right, great. So now you can see how the cache is evolving in this example, and you can see the example of phases, right? So we always have 3 misses per phase. All right. So then again, we need to prove that opt will fault at least once per phase, right? So here we have 2 cases. Okay, there's 2 things that can happen in a phase, right? Suppose that in one phase, the same page faulted twice in the same phase. So what happens, right? So in this case, what do we have? We're going to have that, suppose that R1, okay, so we have here like R1 is the page, is this request 1 is when the page P, okay, so let me say here first, let me write, say that page P faulted twice in one phase, right? So what happens here? Let's just call this page P. So let's say that R1 is the first request, okay, that that page P faulted, like that like we faulted on the same page, like when requesting the same page. Okay, so by that, let me put here, like by that I mean like we faulted when requesting P. Okay, does that make sense? So what we're saying here is we faulted when we received, when we requested page P. And now what I'm going to do is, let's just see what happens in this case, okay? Whenever the R1 is the first request in which we faulted, right? So R1, let me define R1 here, like first request of P that we faulted. Okay, and then what we're going to have is we're going to have a bunch of other requests like R2, R3, blah, 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 RM -1. Okay, so these are going to be like intermediate requests, let's call these. And then at request RM, okay, we requested again page P, okay, and faulted again. Does that make sense? So this is just encompassing, like if the same page faulted twice in one page, well, there's the first time it faulted, and then there's the time right after it that it faulted again on the same page, right? So all we're saying is that encoding this, and this is within a phase, right? So this is all within a phase. Oh, my pen is not working. Phase. Okay. All right, so here's the thing. If we faulted twice on the page, so once we faulted once, what happens here? In this scenario, what happens at this time? At this time, we had no page P in the cache, right? The first time that I faulted, all I can say is that I had no page P in the cache, right? Now, when I fault again, remember, we're using the least recently used heuristic, right? So if I faulted here, it must be the case that I must have requested, like queried, k minus 1, right? Like different pages, right? Because out of the k pages in my cache, right? And in that case, I will remove P. Does that make sense? Because if at request M, I'm getting a page fault, right? Here, once I have P in my page, at some point here, I must have evicted P, right? So must have evicted P. But to evict P, what do I need to do? I need to query all the other k minus 1 pages that were in my cache to begin with. Does that make sense? So that's why, because we must have evicted P. So then we made the k minus 1 request and P became the least recently used, right? So, okay, therefore P least recently used page. Okay, now here's the thing, right? So, all right, so if we did this, what did we do? Well, what does this imply, right? So now this implies, maybe let me put in blue. So this implies that we must have made k plus 1 distinct requests. In this phase. Right? Because what happens? Well, what happens is that why do I have k plus 1 distinct and not k, right? Because we have to look at what happens in the phase. Look, there is this part of the phase and there's this part of the phase. Now, in the beginning part of the phase, we had no P, right? So if we had no P, either we had a page that P replaced, so that was from another request, that makes sense? Like that page was already there from a previous request, right? That we evicted. And then, so we had one page here, right? So where's the k plus 1 distinct pages? So like, let me put here in parentheses, the evicted page at request R1, because we replaced that page with the page P, right? Then we have the k minus 1 distinct pages after R1. And note that none of these are the page P, right? And these distinct after R1, they have to be different than the evicted page, right? Because the evicted page was not there. And then what we have is page P, right? So, and again, I mean, well, this k minus 1 distinct pages here, there is a little bit of detail, but the thing is, if one of these pages is equal to the evicted page, it means that we evicted another page beforehand, right? So like there is always k pages. There were always k pages and P was not there in this phase. Does that make sense? So here we must have made this k plus 1 distinct request in this phase. But here's the thing, right? Like what is the size of the cache of opt? The size of the cache of opt is also k. So if you make k plus 1 distinct requests, opt has to fault at least once, right? So therefore, by the pigeonhole principle, opt has to fault once, right? Because if in any phase I make k plus 1 requests, well, one of these pages are not in the opt, no matter what the stage of the opt was in the beginning of the phase. Does that make sense? Okay, great. So, oh, sorry. My apologies here. Let me just correct something wrong that I said here. So, all right. So what did we do here? Right. So let me do this accounting properly. So we have the k minus 1 distinct pages. We have page P. But the thing is, actually, so we queried all the k minus 1 distinct pages, right? And we also have to remove the evicted P, right? So to evict P, we have to query an extra page. So this is the extra page to evict P. So we have k minus 1 distinct pages after R1, plus the page that evicted P, plus the page that evicted P, plus the page P, right? So we request P at R1 in our phase. Then we do k minus 1 different pages requests that were already in our cache at least. And we have one page that will evict P. This page was not in the cache at all. So that those are k pages, right? So we queried k pages plus we queried P, right? So we actually made distinct requests in the phase. Okay, sorry, I was conflating some things here. So we made k plus 1 distinct requests in this phase. Okay, does that make sense? So now we prove that in this case, if the same page faulted twice in one page, then we know that opt must have made a mistake, right? So that's one. But now there's the other case. And what is the other case? That each page faulted at least once, right? So what happens here when each page now faulted at least once, right? So if each page faulted at least once, what do we do? Well, here's my claim. In the beginning of each phase, the content of opt and of our algorithm, they intersect in at least one page. Okay? So this is the claim about the phase, that they will always intersect. And why is that? Here's the proof. Let's look at the fault in the, let's look at the last fault page in the previous phase, right? So what happened there, right? So we're going to look at one phase, and then this is the current phase that we're at. And we're going to look at the last fault in the previous page, which is the last request, right? So let's say this is request R, okay? So here's what happens. Since opt and A, oh, sorry, yeah, let me finish the proof, I guess. So here, how do we complete this proof? Look at this request, right? So if, well, we know that R, like, let's say they request page P here, right? Like page P. So A faulted at P. So in the new phase, in current phase, and now you see why we're defining the phase that starts after the last failure, right? Like if A faulted at P, in the current phase, the cache of A has page P, right? That we know because A faulted. Now, what happens to the opt? If opt did not fault at P, what does it mean? It means that opt already had P in its cache. And it will continue to have within the phase, right? Like in the beginning of the phase. But if opt faulted at P, then P will now be in opt's cache. So you can see why we're defining the phase this way, like after a failure, because after this failure, we know that the cache of A and the cache of opt, they share one page. So now we know this, we just proved this. Now, since opt and A, they had a common page, then opt must have faulted as well in this phase. Why is that? Because now each page faulted in this phase. So in particular, P will fault. Well, sorry. Well, in particular, how many K, like in particular, we have each. So let me say this. This implies that we have K distinct page faults. Correct? So no matter what opt had, right? So, oops, sorry. Like no matter what opt had before, we will have we'll have K distinct page faults, which means that we will have like K distinct queries, like distinct requests, like page requests. Right? So if we have K distinct page requests, right? And all of these faulted. Remember, now opt and A had a common page. So opt could only have already had K minus 1 out of the K pages that were requested. Does that make sense? Because what is the way? So let's look at at each different page. So we have K different distinct pages that faulted, right? Like let's say P1 up to PK, right? Those pages are distinct. Now, what is the only way in this phase for opt to not fault? Is that the cache of opt would have to be P1 up to PK. Does that make sense? But we know that P1 up to PK does not contain the page P, right? Because each page faulted in this phase. So in particular, P also faulted, right? So this is a contradiction. Does that make sense? Because let me just move it here. Like if you think about it, let me just write it succinctly. Oh, let me decrease this. There we go. Right? So in the beginning, if opt like cache is P1, P2 up to PK, right? Like it cannot be, right? So let's say that P1 up to PK are the faulty requests. And we know by this point that PI is different than PJ for I different from J. Now, the only way that opt does not fault is if opt's cache is exactly P1 up to PK. But we know, like in the beginning of the phase, right? Like in the beginning of the phase. But we know this doesn't happen. Because P is in the cache of opt. And P is different from the PIs. Right? And the reason why P is different from the PIs is because, remember, we're using the least recently used heuristic. Right? So that is something for you to show. I'll just leave the detail for you to show, right? But that's why the P's are different from the PIs, okay? That's why we have a contradiction. Now, all right, so now we proved an upper bound. We proved that the least recently used is at most K competitive, right? And now let's just show a lower bound for deterministic paging algorithms. And how do we prove this lower bound? Well, the theorem is the following. Any deterministic algorithm for paging with K pages is at least K competitive. So this is showing that like this algorithm is optimal, right, in terms of competitiveness. So, and how do we prove this? Well, how we usually prove stuff about online things, right? The proof is a proof by trolling, right? So there's a common lower bound technique for online algorithms, also commonly used technique online, right? Like people troll people all the time on the internet. So, all right. So let's say that we have just K+1 pages, okay? All we need is K+1 pages. And let's say that A is our paging algorithm, okay? So here's the input sequence. And why is the proof by trolling? We're just going to troll our algorithm A. What we're going to do is the input sequence will be at each step, we're going to request exactly the page that our algorithm does not have. Okay, that's the intuition behind the trolling, right? So really trolling the algorithm A. Now what happens? A will fault every single time, right? Now, what is the offline algorithm? Well, the offline algorithm will just do what? On a cache miss, it will just delete the page that is requested furthest in the future. Does that make sense? So, and here the offline algorithm, it knows what the sequence is that is going to mess up with A, right? So we have the sequence because A is deterministic. So once I make the queries, I know exactly what the next query will be, right? So the offline algorithm will just look at those queries and say, you know what? Whenever I have to have a cache miss, I'll just delete the page that I know, because I can see in the future, the furthest one that will be requested in the future, right? And now, well, what happens? So when the offline algorithm deletes the page, its next delete happens after at least K steps, right? Because now I received my new page and I have my K, suppose I have my K pages. I received the page that was not there. And now I look from all of those pages, which one will be requested latest in the future? And then I replace it. When am I going to miss again? Well, after I see this first K-1 pages that I didn't delete, they have to show up before my next fault. So every time the offline algorithm deletes a page, its next delete happens exactly after K step, or at least after K steps. Because I have to see any of the other pages before I see the page in which I'll fault. Right? Otherwise, the algorithm would just have flipped who is the furthest in the future. Does that make sense?
But even the offline algorithm should also always miss, right? Because you're always querying someone that's not in the cache.
Correct. And that's why, and that's another example of why we need to do a competitive only against the best algorithm that we could have, right? Is because here the cost, like if you look at the cost, right, like it's kind of going to infinity for any algorithm. You'll always miss no matter what, right? Like there's no algorithm that never misses, because if you query K+1 pages, any cache will miss once. But all we're saying here is that, you know, A faults every single time. This is an input sequence that A faults every single time, and the opt faults every K steps. Right? So A is faulting at least K times as much more than the offline algorithm is faulting. Does that make sense?
So it's for that input sequence for which A faults every time that the offline algorithm succeeds. But
Sure.
I guess the offline algorithm can, there is like another input sequence where the offline algorithm also like misses every time.
Well, no, because for that's the thing. The other input sequence, the offline algorithm will see which page to delete and can use it, like, and can use the same strategy, right? Because if you give the input sequence, and remember, the offline algorithm can see the input sequence in advance. So the offline algorithm will always has the benefit to do this. right? On a page miss, I'm like, oh, okay, I'm just gonna delete the page that's gonna be requested late furthest in the future.
So it's like saying if you have k+1 different pages, then like the offline algorithm costs at most, number of total requests over k. Like it fails at most once every k steps because you can just choose to like, kick out the one that'll make you fail last.
Exactly. Like between one fail and another one, we just proved that no matter what your input sequence is, you'll have to query everybody else, right? Like, because you know what the input is, right? Like you know exactly what the furthest in the future. And that's why I highlighted it in blue so that you know that this is the difference. This is the power that the offline algorithm has, right? So now you see the lower bound. So now we have the upper bound that we have a k competitive algorithm, and we can see that this is the best we can do. Okay. Okay, great. So, all right, so let me conclude because I'm already like over time. So, all right, so what is the conclusion? So online algorithms are important for many applications, right? When we need to make decisions right when we receive the information. We saw there's all these exciting applications, and we saw like pretty much 3 of them. And we learned about the competitive analysis, right? Which is how we can benchmark how good our algorithm is, right? And yeah, that's it. And so this lecture, if you want to know more, here's all the resources that I used to base my lecture on. And also like, if you look at the book by Motvani and Raghavan, okay? So that's it. Let me know if you have questions. I'll stick around. Otherwise, the lecture's over.